Hello students, welcome back for this class after a very long time, and today we are going to discuss the genius of the Slater's rules. As we all know that Slater's rule is very much important for determining the effective nuclear charge of the electrons in the shells. So this is really a very great method for finding the Z effective, yes, and Z effective is further important for finding your electronegativity and for finding ionization energy and much more. So let's see how it works. So we know like the effective nuclear charge is what? It is the tendency by which uh, the protons, the protons inside the nucleus attracts the electrons in the shells. Yeah, so it is just a pull of the nucleus felt by the electrons revolving in the shells. So with distance, it decreases because it's a short range force. And let's see. So we know like Z effective, is Z minus S. We say Z minus S. Now this is the Z effective, the actual Z effective, which we are going to calculate. Yeah, which we have to calculate. We have to calculate this thing. And the other one, the Z, the Z you are seeing, Z, this is just like the number of protons. Yeah, so this is easily like we can find out using atomic number. And the S is known as the screening or shielding constant. You can say like screening constant. It's a constant. Yeah, it's a constant, and we will see like how it will be determined. So Z effective we have to calculate it. Yeah, Z we know the number of protons. The only thing we have to know is the screening constant, like how to find it out. So let's explore. So it's a very short method. So let's see. Here we go. So are you excited? I hope you are. Yes. We are meeting after a long time, and it's really a very exciting topic. Okay. So we start here. So we know like we have to like first of all we have to write the electronic configuration, write electronic configuration of the element. Yeah, and we have to group it and group it. Now this grouping is something different. We have to learn it. So let's see. Suppose we take an example of chlorine. Yeah, chlorine Z is 17. Now for chlorine we know it is 1s2, 2s2, 2p6, 3s2, and 3p5. Yeah. Now we have to group it. So grouping means like you can say like 1s2. This is one shell. Yeah. Then 2s2, 2p6 coming in the second shell. Now then 3s2, 3p5. So like that. So this is grouping. Yeah. And if we go further, you can like suppose we can take another example. Like suppose we are taking iron. Z is 26. So we will take 1s2, 2s2, 2p6, 3s2, 3p6, and then we have like 4d. Sorry, we have 4s2 and 3d6. Right now, we have to group it again. So 1 and then 2s and 2p. Then we have 3s and 3p. Yeah, 3d will be alone and 4s will be with 4p or whatever you want to take. But actually the configuration is this, but when we group it, yeah, we have to write 3d first because the third shell and 4s2. Yeah, 3d will be first and then 4s2 or 4p, whatever it is, like that. Okay, so this is how, this is not electronic configuration, this is after grouping. Yes, in electronic configuration we write 4s2 3d6, but in grouping like we are just following the numbers. Yeah, 1 2 3 4 like that. Got it? And 3d is separated like d and f. Like d and f you have to separate them. Yeah, their grouping should be done like separately. Like suppose if d comes, it's 3d. Suppose if f comes, it should be 4m, just like that. Yes. Okay. So we have to group it. This is the first right electronic configuration and group it. I hope it is by you. Yeah. And of this meeting, like in the end, towards the later end, we also doing some problems. Yeah. So that everything is clear. Now, after grouping, what we have to do? Now we have to find out the S. Yes. And suppose like we have been asked like, okay, find the contribution for the p electron. Yeah. So we have to make sure like we have to always look towards the preceding electron. Yes. Not on the right side like 3d 4s2. So we have to always look towards the backward direction, the contribution. Yeah. Okay. So not the electrons higher than this like 3p, like we go to 3d or 4s or whatever. Okay. So the second point. Now, after we have done all the grouping, now we have to consider any whatever the desired orbital is, like whether ns or np electron. Yes, consider a particular ns or np orbital. Okay, now after watching all this video, now you will be able to like find out the z effective values by your own. Yeah, so you have to wait for a while. Yes. So here comes the interesting part. Yeah. So the contribution, yes. So if we are finding for like s and np orbital, yeah. So then uh, this orbital like ns and np. Suppose like we are looking for beryllium. Let's say beryllium. So beryllium is 1s2, 2s2, right? Beryllium is 2, 2. So 1s2, 2s2. So if we are found like 1s, this is the grouping. Now if we are founding for this, yeah. So a single s electron, yes. So if we are finding for a single s electron, so what we have to do? We have to use this rule, yeah. S is equals to 0.35, yes. For other electrons in ns and p. Okay, this is very important, like for other electrons in ns and p group. So like one electron we have to leave, yes. So in this, like we can see like in ns and p, this should be considered as ns and p. P is not there, okay, and this will be considered as n minus 1 s or n minus 1 p, right? P is not there, so n minus 1 s. So here the contribution from one electron, because one we have to exclude, so it should be 0.35. So they say like for other electrons. And the B part, the second part for this. Now once we are done with ns and np shells, yes, we have to move towards the preceding shells. Yeah. So now move towards the n minus 1 shell. So their contribution will be how much? 0.85. So what does it means? It means like for 1s2, what you will be having? For 1s2, there are 2 electrons, so 2 into, and because it belongs to n minus 1, so you 2 into 0.85, and that will give you how much? 1.70. Now in case if there is another shell like n minus 2 shell or lower shell or any lower shell n minus 3 or whatever, so for those all electrons you have to take s is 1.0. Yeah, s is 1.0. So that's it. Yeah, this is especially for ns and np orbitals. Yeah, we are not talking about d or f pairs. For d and f we have to study separately. Yeah, another assumptions and the rules. I hope this is clear to you. So I'm just again revising. Like first of all, you have to identify your NS or NP orbital, and then for NS and NP electron, all those electrons which are belonging into this sets of orbitals are going to have the S value 0.35. Right. Now, if we move towards the uh, next lower or shell, that is n minus 1 shell. Now for all those electrons which are belonging to n minus 1 shell, the contribution will be 0.85 per electron. And similarly, if we move towards more lower shell like n minus 2 or even lower, then it is for 1. Yeah, the contribution is 1. And now what you have to do now, we know the formula Z effective is equals to Z minus S. Yeah, so Z for beryllium was 4. And here what it comes like the S value from 1s2 was 1.70 and S value 1.70, and for 2s2, like for 1 electron, it was how much? 0.35. So if you do some mathematics here, you will find like 4 minus 2.05, so it will give 1 point. So that is your Z effective value for beryllium. Yeah, and that resembles a lot with the experimental value. Okay, so this is how like we can find out the Z effect. Okay, now we will do like one more problem. Yes, because doing this is not enough. Yes, so I'm just moving all this. Yes, I hope it's clear to you. Now we will be doing for one new element, and let's take chlorine this time. That is equals to 9, that is chlorine. So we have 1s2, 2s2, 2p6, and then 3. Sorry, counting goes on. 2p5, right? So we have to find for 1 electron for a 2p electron. Yes, for a 2p electron. So again, let's do the grouping. Okay. Then we have, this is NS, NP, and this can be considered as N minus 1, S or P, whatever it is. Yeah. So now we know like NS and P, the contribution is 0.35 per electron, the rule number A. Yeah. And for the preceding cell, it should be 0.85 times 2. So how many electrons are there? So we have 0.85 times 2, right? And here we have like 7 electrons, but 1 we have to exclude here. So we have 6 into 0.35. And that will give me how much? So let me use my calculator. So 0.85 times 2 is 1.70. We've done. And then 6 into 0.35 is 2.10. And then adding both, I'm getting 3.8. Yeah. Now the rule was Z effective is Z minus S. So this was the value of S we have calculated. So Z was 9 minus 3.8. So it will be 5. And that's the that resembles the actual Z effective, which is stated for chlorine. So tell me like how this rule is, yeah, and whether you are able to find out the values. And this is very, very important, like for competitive exams like JEE Advanced, JEE Mains, and even other competitive exams like JAM. Yeah. So this is really, and we should also learn these things like for our curiosity. Yeah, this is a good thing to learn. Yeah. So it's a nice add-on for you. And now the rule number third, and this is for like if ND and NF orbitals are also there. Yes, ND and NF orbitals are there. So ND or NF, yeah, orbitals are there. So let's see. So what we have to do, a grouping we have already discussed. So in this, the rule number A is like each each of other electrons in ND or NF contributes S is equals to 0.35. Okay, so this remains the same, and then the other preceding orbitals or electrons in lower group will be given 1 point each of the electrons, right? So very simple, very simple. Okay, so let's do just a single problem on the basis of this. Now we have all heard about vanadium, the V, and the Z is 23. Is 23. And now we have to calculate the Z effective for a vanadium atom for a 3D electron. Let's say for 3D electron. First of all, we have to write the configuration. 1s2, 2s2, 2p6, 3s2, and then 3p6, 4s2, and 3d3, right? So this is the actually electronic configuration. Now, but we have to do grouping. Now in grouping, I told you like to increase by the numbers. Like so, 1s2, we have this group. Then 2s2, 2p6, we have this group. Then we have 3s2, then 3p6, and we are not including 4s2 here. We are just saying 3d3. Yeah, so 3p6 and then 3d3, and then we have this 2. Right? So now what to do? We have to, again, we have done all the grouping and we have to calculate for the 3D electron. That means the electron which is here. So obviously we have to exclude this one. Yeah, the one electron. So we have for other two electrons, we have 2 into 0.35. As per the rule stated for NS, ND or NF. Yeah. So for each electron contributes 0.35 and the other electrons, lower group, contributes 1. So for all these lower electrons, which are 18, the count 18 into 1. So 18 plus 2 into 0.35, so 18.7. Okay, so this is the S we are having. Now we very well know like Z effective is equals to Z minus S, and Z is like 23 minus, and we have S is 18.70, and we get something around. Okay, make sure like this is for the D electrons, yes, not for the S one. Okay, now suppose you have been asked to calculate for the 4s electron. For 4s electron, this is the same thing. Okay, so again the same thing we have to do. Just taking like just copying this, and here we go. Okay, now but if we have to calculate for the 4s one, now we have to follow the rule of the first rule, yes, or like NS NP orbitals. Yeah, okay, are you getting it? So 0.35 into 1 for this one, yeah, and 0.85. So we have like 3, 3, 3. So this is the same, yeah. So we have 6, 7, 8, 9, 10, 11. So 11 times 0.85. And then for these all like, yeah, lower orbitals, we have like 6, 7, 8, 9, 10 into 1. Yeah, so we will get 10 plus, and we have, just a second, 11 into 0.85. So we have 9.35 and we have plus 0.35. This total will give me 10 plus 9.35 plus 0.35. So will give me 19.7. And if we find Z effective, it should be Z minus S, that will be 23 minus 19.7. And that will give me something around 3.3. This will be our So I hope it's quite easier. Now see, the beauty of this is like you can see the 4s electrons are having a nuclear charge of around 3.30. Yes, the 4s electrons are having nuclear charge of 3.30. That's the beauty of this Slater's rule. Yes, so why it is so much important. Yes, and why it has a lot of advantage to understand the chemistry. Yes, and if you find for the d electron, it is 4.30. Yes, the nuclear charge is 4.30. We have calculated. Now, like we know the ionization energy. It is the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. Yeah, the energy required to remove an electron, just like that, from the outermost shell. So we can see like the nuclear charge felt by the electrons in the d orbital are 4.3, and in the s orbital is 4.3. In the outer s orbital is 3.3. Now the nuclear charge is more in the d orbital than the s orbital. So let us take let us take a small pause and just think that from which orbital it will be easier to remove electron from vanadium, whether it should be 4s or it should be 3d. Think on it. Yeah. So I think like you have already the answer with you, and obviously you will say, and every one of you will be saying, like it's 4s because the nuclear charge is very low. Yeah. So it's easier to remove electron from the 4s than the 3d. And that's why, like when we write the vanadium plus, yeah, like one electron gone from the vanadium. So we just write like 4s1, 3d3 instead of writing like 4s2, 3d2. Are you getting it? So it's very, very interesting, this Slaters rule, and I hope like you have understood it, and you need to practice a bit. Yes. Uh, to get to all the answers, yeah, you have to practice a bit, and that's it from my side. Please do comment and tell me like how you liked it, and your reviews and your comments are always a token of motivation for me, yes, to do better, to improve. Yeah. So thank you very much. And in the next, in the upcoming video, we will be discussing like why the off-by rules, yes, and the Slater's rule like complements each other. Yeah, we will look into it. Yeah, like why the in electron